Well, this is video number 34. This is oscillations in one dimension, and I'll define what an oscillation is in just a moment. But first, I'd like to take you back to when we were talking about springs. We were talking about elastic objects in general, especially those that followed Hooke's law. And the whole idea of an elastic object or a spring is that it exerts a restoring force. The whole point of the restoring force is if you stretch the object in one direction, it exerts a force in the exact opposite direction, trying to restore itself to its original shape. So if you were to imagine most springs, for example, a slinky is a giant spring. If you were to stretch it, when you release it, it snaps back to its original position. But it doesn't really have the ability to be compressed. A slinky's natural position is with the coils resting right up against each other, so you can't squeeze it in tighter. There's also springs that, for example, like inside a clicky pen, if you were to take the spring out of this and compress it, you would find that it pushes back and restores itself to its original position. But it's not very good at responding to being stretched. If you were to take the spring out of a click pen and stretch it, you pretty much break it. They don't obey Hooke's law for stretches. So we talked a little bit back in Hooke's law about how you have different types of elastic materials or springs. And for this topic, I'd like you to imagine a spring that is sort of idealized, meaning it responds, according to Hooke's law, if you compress it or if you stretch it. In either case, it will respond to Hooke's law. And there are springs like that out there, but I want to emphasize if you are familiar with real-life springs, you're probably familiar with ones that do one or the other, stretch or compress. And we want to talk about the type that does both, because they'll model something very important for us. So I'm going to use this animation from Flipping Physics to explain what I'm talking about. He stretches the spring a particular distance, and a force then in the spring pulls back the other way. And when you release the block, it doesn't just return the block to the equilibrium point, that blue dotted line where it started. You can see again, it starts on the blue dotted line, and he pulls the block to the side. When he releases it, the spring energy turns into kinetic energy, and it doesn't just go away when it hits that blue line that it had returned to. So it actually overshoots where the spring would want to be. The stretched spring becomes a compressed spring precisely because the potential energy becomes kinetic energy, which has to then go somewhere before the block can stop. So it goes, if he were to just let it go, it would go back and forth between stretched and compressed and stretched and compressed. And in an ideal situation, it would just do that forever. This is a video of me modeling that with two different stretching springs. I used one on either side. And the reason I used one on either side is that I didn't have a good spring that stretched and compressed, but I wanted to demonstrate that motion is what we call harmonic motion. It is repeating, and it's repeating every certain period of time. The amount of time it takes to complete one cycle is the amount of time it takes to complete the next cycle. So that is what we refer to as harmonic motion. And it is also what we refer to as oscillation. The cart was oscillating, and in the previous slide, the block had been oscillating, or would have if the video had continued, meaning that it continues to pass through an equilibrium position. It goes through it to one side, and then it goes through it to the other side. And in an oscillator, you have kinetic energy being exchanged back and forth with a specific type of potential energy. In this case, elastic potential energy, spring potential energy. I'd like to show you a lab I did with that video. I opened up Logger Pro and I inserted the video, and then I used this function down here to tell Logger Pro that I wanted to measure the motion of this object in the video. So first I use this little tool to tell the computer how big something in the video is, so it knows what the distances it's measuring are. And then I just went in and started adding data points. I picked a part of the cart and I picked a starting point. I picked the bottom left corner of the cart just because I needed one spot. It doesn't matter where. As long as I kept picking that bottom left corner, you can see each frame I'm clicking that bottom corner and telling the computer at this time the object was here, and at this time the object was here. And it's tracking the X and Y positions. Now the cart's not moving in the Y direction, so I actually went in and removed the Y component off the graph. We don't care about the Y. But in the X direction, the graph you just saw there were the data points of the X position of this cart as a function of time. And as I kept going through this, through multiple oscillations, I added more and more data, and you can see that the shape of the cart motion versus time graph became repetitive. In fact, let's jump forward a little bit here to about here. Okay, so now on the video, you can see all those little blue dots. Those little blue dots are all the positions that the cart has been in over a period of time. So you can see it's not displacing very far. It's just continuing to move back and forth through this one little area. And you should be able to see the density of the dots is a little bit heavier on the ends and a little bit thinner in the middle, meaning that on the end it travels less and less distance, which is obvious if you watch the video because the cart slows down on the end and moves fast through the middle. But the graph that's forming in the background there, if you see that, that is a sine curve or a cosine curve, depending on where exactly it started. They're the same shape. And in fact, this one will happen to be a cosine curve because I just happened to choose to start the cart at a maximum position. I started it on the far right. So when we see that background graph, we're going to see that it is a cosine curve right there. We're also going to see that I can look at the velocity in the x direction, and that is also a sinusoid, although it's a little bit different. It's a negative sine curve. Yeah, let's take a look at this. This is the position versus time graph. Notice the axes. This is the position versus time graph. Also notice it doesn't start at 0, 0. It didn't start at 0 seconds because the cart wasn't in motion at the beginning of the video clip. So I moved forward to about a second and a half, I think, before we started taking data. Notice there's not a 0 position on this. And that's because the computer understands 0 position to be the far left of the screen, and the cart never reached the far left of the screen. So it's giving me that it went back and forth between two positions, somewhere around, looks like 0.22 meters and 0.6 something meters. The 0.6 something meters from the left is the maximum position that the cart had, and that's where it started. As it went from the maximum right position to the maximum left position, as far left as it ever traveled in the video, what direction was it traveling? Well, if it was starting on the far right and it wound up on the far left, clearly it was traveling to the left. And when an object is traveling to the left, what can you say about its displacement and its velocity during that period of time? An object traveling to the left, we typically say, has a negative velocity, which should be obvious from this graph because velocity is the slope of a position versus time graph. The slope from max right position to max left position here is definitely a negative slope. It varies. It's steeper in the middle of that period of time, and it's closer to 0 when you get right to the max left position. But that's a negative slope, so negative velocity the whole time. The same thing would apply in reverse when you say the object went from the maximum left position to the maximum right position. As the cart moved back to its original position, it clearly moved to the right to go from the left side to the right side. So its velocity would be to the right during that period of time, meaning its velocity is what we would call positive, and the slope of this graph is positive. So as it went back and forth between the max left and the max right, it takes equal amounts of time. You can see the spacing on this graph, equal amounts of time spacing out each of the max right positions. That is the period. And you can see that the velocity goes from being negative to being positive to being negative to being positive. But also, when we pull up the velocity graph, we can see that the velocity went from being a lot to a little. It went from being a lot negative to 0 to a lot positive to 0 to a lot negative to 0 in a sinusoidal form. This is a characteristic of oscillators, is that the position, the velocity, the acceleration, the net force on them all follow a sinusoidal form over time. If we were to pull up one section of the velocity versus time graph and take the integral, here it says that the displacement of the cart from its 0 velocity back to its 0 velocity again was 0.35 meters. So that would mean that the cart was moving back and forth 0.35 meters from one extreme to the other extreme as it was moving from right to left or left to right. And if we pull up the position graph and check what was the maximum it went from left to right, it has a minimum position of 0.238 meters and a maximum position of 0.597 meters. And that matches up. That's the exact same amount of displacement that we got from the integral from the previous graph. We're not going to be spending time with me asking you to do that type of integral, but I wanted to emphasize that all of the stuff we learned about kinematics earlier still applies to a situation where an object is following this oscillation, this sinusoid pattern. If we were to do a curve fit of the graph, we would find that it is a sinusoid. The computer matched it up really well. And if I were to take a look at this image right here, we would see when the cart is at its maximum right position, when it's right there, it's at its maximum displacement. What is the direction of the force that is on this cart? The cart is about to be accelerated in the opposite direction because there is a net force applied in the opposite direction. So this is the spring that is causing it to do this. So it is still following Hooke's law. The calculations for it would be a little bit complicated because the force is constantly changing. So that means the acceleration on the cart is constantly changing. When it's at the maximum distance in the other direction, a displacement to the left, then a force to the right. We don't want to have to do math with a net force and therefore an acceleration that is a sinusoid function. All of our kinematics equations work best with a constant acceleration. So taking the kinematics equations we've used and throwing them into here would be a little bit problematic. But understanding that conceptually everything that we've learned still applies, I think is an important point to understanding oscillators. And of course, when the cart had no displacement at all, there was no net force on it. But that doesn't tell you what the speed is. If you know that the net force on an object is 0, you don't necessarily know how fast it's going. And in this situation, our system, if it had 0 mechanical energy, then the velocity would be 0. But in this situation, I had set the cart in motion. Our system had mechanical energy. It was just oscillating back and forth between being spring energy and kinetic energy. So when it was right here in the middle with no displacement and no net force, it was moving at its maximum speed. It had kinetic energy. And that's the big point that I want to get across with oscillators is because we can talk about conservation of energy, we know that the potential energy and kinetic energy equations are pretty straightforward. They're not too complicated. We know that the potential energy is maximized at a full compression of the spring or a full extension of the spring because it will compress and stretch the same distance if we have an idealized spring. So x to the left of equilibrium and x to the right of equilibrium are the exact same for this idealized spring. So on either side, at the far left or the far right, you have the maximum potential energy stored in the spring, and then in the middle you have maximum kinetic energy. It's going fastest in the middle. And you can therefore say a lot about how fast the cart is going if you know how far the spring was stretched, and vice versa. We've already done a little bit of that. The maximum amplitude that the spring compresses or stretches, that's the term we use for its maximum stretch. So at any given point, it has some stretch or compression that you would refer to as its delta x or its delta L, depending on how you're talking about Hooke's law. But its maximum is referred to as the amplitude. This animation is also here to point out that you can model an object moving in circular motion as being in simple harmonic motion. It is a type of harmonic motion. The mathematics of it would get a little bit more complicated, but the mathematics of it would end up being the exact same as what we're talking about when we're talking about an object going back and forth in one dimension. Okay, so we do want this conceptual understanding of what happens. We also want to have a conceptual understanding of something like what happens if I increase the K of the spring, if I put a stiffer spring in, or what happens if I change the mass of the system or certain other variables. Changing the amplitude actually doesn't matter. If I move the cart to a smaller degree, then only the amplitude would be affected, not the period. But let's take a look at what happens if I change the mass of an oscillator. Clearly, lowering the mass had an effect on that oscillator. Part of the reason that we want to make sure that we understand this is that a more complex three-dimensional version of an oscillator is how scientists model the behavior at the atomic level of any solid object. And while we're not going to take it that far, we do want to understand that this is the basis of it. So what is it that you're actually going to be asked to do? We have a couple of equations that I want to point out. Notice this top one, the displacement in a harmonic motion as a function of time is this cosine function. I'm not going to ask you to do calculations with this cosine function. It's not beyond us. We're just not going to have time to spend time on it. The velocity equation also is a sinusoid. For those of you who have taken calculus, you should recognize that the velocity function is the derivative of the position function. The derivative of cosine is negative sine. We are going to point out that velocity max in the second line there being equal to the square root of k over mx, where that x is the amplitude or the stretch of the spring, you would be able to get that from doing a potential energy to kinetic energy equation. And this bottom one here, the acceleration, is another one that if you've taken calculus, you would recognize where that comes from. And if you haven't, then don't worry, because these three equations, the cosine, negative sine, and negative cosine ones here, we're not really interested in spending time on these. Again, they're not that difficult, but we just don't have time in this course to spend time on that. What we will spend time on is this. The period of oscillation for a simple harmonic oscillator is going to be determined by this equation right here. 2 times pi times the square root of the mass of the oscillator divided by the k, where k is the spring constant. And if you have something like for example, atoms in a solid, then obviously they're not connected by actual springs, but you can determine what the effective spring constant of that situation is by experiment. We'll also talk about frequency, which is equal to 1 over the period. So that's over there on the far right. Because frequency is 1 over the period, that means period is 1 over the frequency. So going back and forth between those two is something you'll want to become familiar with. And all that means is, especially for smaller periods of time, you want to sometimes talk about the frequency of oscillation more than the period. If something is oscillating every 1/8 of a second, then that means its frequency is that it's oscillating 8 times per second. And this equation is just a way to go back and forth between those two different ways of saying the exact same thing. The units of period are seconds, so the units of frequency are 1 over seconds. And you can always write the units as 1 over seconds or seconds to the -1 power. A lot of times scientists use the unit hertz, capital H, lowercase z. The unit hertz just means 1 over seconds, and it's used for frequency. Please be careful that lowercase f for frequency is also the lowercase f that I used for friction, and those are obviously not the same thing. So in context, that's really obvious, but let's keep that in mind. All right, that's it for this video. I'll come back and do some more to talk about oscillations and, more importantly, what you would be expected to be able to do with oscillations.